Hello everyone, and welcome back to my channel. This is Vishnu Anjipudi, and today we will be solving problems 21 through 25 of the 2018 AMC 8. Let's begin with problem number 21. How many positive 3-digit integers have a remainder of 2 when divided by 6, a remainder of 5 when divided by 9, and a remainder of 7 when divided by 11? First, we note that 2 is 4 less than 6, meaning the number has to be 4 less than a multiple of 6. Okay, so mult just stands for multiple. So additionally, we know that 5 is 4 less than 9. So we know that it's also 4 less than a multiple of 9. And 7 is 4 less than 11, so we also know that this is 4 less than a multiple of 11. So because it's 4 less than a multiple of 6, 4 less than a multiple of 9, and 4 less than a multiple of 11, we know that it's 4 less than a multiple of the LCM of 6, 9, and 11. And this is because if you just add 4 to the number, you get a multiple of 6, a multiple of 9, and a multiple of 11, which is a multiple of the LCM. We know that the LCM of 6, 9, and 11 is just going to be 6 times 9 times 11 divided by 3, since there's a common factor of 3 with 6 and 9. And this is going to give an answer of 198. So since we know that we want 3-digit integers, we have that the numbers can be 198 minus 4, or 194, 198 times 2 minus 4, which is going to be 392, and then we can add 198 to that to get 590. Add 198 to that to get 788. And then finally you get 986. A total of 5 numbers. Shown here. Problem number 22. Point E is the midpoint of side CD in square ABCD. BE meets diagonal AC at F. The area of quadrilateral AFED is 45. What is the area of ABCD? So first of all, we know that E is the midpoint of side CD. So we have DE is going to equal to EC. We also know that the area of quadrilateral AFED is going to be 45. And that BAC is the diagonal of the square, and BE is just connecting a corner to the opposite midpoint. So, first of all, we know, let's just denote the side length of ABCD as S. So, we know that by similar triangles, ABF and EFC, and since AB is going to equal S and EC is going to equal S over 2, we have the AF over SC is also going to be 1 over 2. So we have AF is going to be S root 2 divided by 3, except 2. And since the total length is S root 2, and then this length is just going to be S root 2 over 3. Now here, we can draw a triangle here. It's similar to the large triangle. So we know that the altitude is just going to be s over 3, which means that the area of this entire triangle, EFC, is just 1/2 times s over 3 times s over 2, which is just equal to s squared over 12. And we know that since the total area of ADC is s squared over 2, we know that s squared over 12 plus 45, which is the area of that quadrilateral, is going to equal to s squared over 2. So from this, we know that s squared plus, we're multiplying both sides by 12, so 45 times 12 is simply 540, and this is going to equal to 6s squared. So we have 5s squared equals 540. So s squared, the area of the square, is 108. Choice B. And now, on. Okay, problem 23. From a regular octagon, so you know it's regular, the triangle is formed by connecting 3 randomly chosen vertices of the octagon. What is the probability that at least one of the sides of the triangle is also a side of the octagon? So this is going to be a lot easier with complementary counting. So again, we know that probability is just number of success over number of total. And here it's a lot easier to use complementary probability, which is just 1 minus failures divided by number of total, since number of failures and number of successes add to 1. So it's relatively just simple to count the number of failures. So there are 8 ways you can choose the first vertex, and then from there we can do casework. So we first know if the first case, we know that the second vertex is one of these two. So if we draw here, we get 2, and then each of these cases would result in 4 more vertices that you could choose from. This one, this one, this one, and this one for this case, and these 3 and that one for this case. So we have 2 times 4. Now for the next case, we have these 3. Now these 3 don't overlap with this first one's neighbors, which are these 2. So we have, this is 3 times, then each one would leave 2 remaining choices. And this is simply equal to 8 times 14 equals 112. And this is when order does matter, so we could use the same technique for the denominator. Okay, so for the denominator, we see that in total there are 8 times 7 times 6, which is going to equal 336. So our apparent answer is 112 divided by 336, which isn't any of these choices. So again, we employ a common math solving strategy, which is to check back your work and see what could have went wrong. Of course, the complementary probability in this case would be 2/3, but that's still not an answer choice. So, what's wrong here? Well, the problem is we included order, but we didn't adequately make calculations. Because otherwise, 80 times 14 would indeed be a multiple of 3, since there are 6 ways that a set could be chosen. So, let's try to work out where the problem is. Here, we have 2 choices indeed, and from that point we have 4. Where if we get one of these 2, we have 2 choices. So first, the problem is not apparent. Here we can see that 5 have been taken. So here, it's not actually a 4, it's a 3. Since you can't, here, you can only choose one of these 3 points. And not this one, because that one's a neighbor. We forgot to include neighbors. So it's actually 2 times 3 plus 3 times 2, which in this case is just going to be 8 times 12, 96. So our actual answer is 1 minus 96 divided by 336. 96 divided by 336, when simplified, is just going to equal to 2 divided by 7. This means that our answer is 5/7. Choice D. Problem number 24. In the cube ABCDEFGH, with opposite vertices C and E, J and I are the midpoints of edges FB and HD respectively. Let R be the ratio of the area of cross-section EJCI to the area of one of the faces of the cube. What is R squared? So first of all, what's the most important thing to note is that the EJCI is a rhombus. This is because CJ is equal to CI is equal to IE is equal to EJ. The area of the rhombus is half the product of its 2 diagonals. So let's calculate the area of this rhombus. Let's first denote side length of the cube as S. So let's look at CD. Let's first find the length of CI, and we'll know the rest of them from there. So we know that CD is S, ID is S/2, because I is the midpoint. Thus we have that CI is going to be S√5/2. So now we know the sides, but that's not actually important to finding out the area of the rhombus. What is important are the diagonals, IJ and BC. Well, we note that IJ is the same as BD, which is just since I and J have the same vertical coordinate. This means that JI is just going to be S√2. Now if we look at EC, this is just the space diagonal of the cube, or side length √3. Thus, the area is S² times √2 times √3, all over 2. This is just S² √6/2. The area of one of the faces is S², so the ratio is just going to be √6/2. Squaring that, we get that the ratio squared is going to equal 3/2. Choice C. Problem number 5. How many perfect cubes lie between 2 to the 8th plus 1 and 2 to the 18th plus 1 inclusive. So first of all, we note that 2 to the 18th plus 1 is 1 more than the perfect cube 2 to the 18. 2 to the 18 is just 2 to the 6th cubed, which is going to equal to 64 cubed. So next, let's look at 2 to the 8th plus 1. 2 to the 8th plus 1 is equal to 257. 257 is going to be less than 7 cubed. This means that all cubes within the range of 7 cubed to 64 cubed inclusive are counted. This is a total of 64 minus 7 plus 1 equals 58 cubes, choice E, and we are done. Thank you so much for watching this video, it really means a lot. Please don't forget to like, share, and subscribe, as well as click the bell icon. As always, if you have any questions, comments, or concerns, please post them down below, or email me at steamaspirations@gmail.com. This is Jishima Jufudu, signing off. Bye.